All right, the third example here we're going to look at is the case of Brownian diffusion. Now, Brownian diffusion does get used all the time. In fact, if you're looking at those models that they've made involving coronavirus, those coronavirus spreading models are actually described in this exact same fashion, using a Brownian style diffusion. And you just assume that people are Brownian particles as opposed to here. But for this example here, we're going to be looking at RNA as a Brownian style particle. So the idea here is you're told that there's some RNA that is released from a virus. Uh, you're told that in 25 nanoseconds, it spreads out an average distance of 200 nanometers. Now, when dealing with RNA or any type of Brownian diffusion, you need to know something about how it spreads. What you need to know is how many dimensions can it spread in. So here you're told that it spreads out spherically. This is actually important for solving this problem. And what you might be asked is, how long on average would it take to reach all areas of the cell? In other words, how long would it take to spread out a total distance of 50 micrometers as opposed to 200 nanometers? And this is something you can do. The idea or the thing that's going to link these two cases together is the diffusion coefficient d here. So you can use the top case here to find d, and then we're going to use d, putting this thing all together, to figure out how long it would take to spread a differing distance. So what we're going to do here is we're going to use this. However, the very first thing we're going to deal with is the spreading. You're told it spreads out spherically, so it spreads out in all dimensions. This is actually important. In the Brownian spread equation, if it's allowed to spread out spherically in all dimensions, it is allowed to spread out in 3 dimensions. So n is going to be equal to 3. This will differ. If your system can only spread in 2 dimensions, like on the surface of a lake or something like that, n would only be 2. So you need to know how it spreads out. Now, using the first set of numbers that we've been provided with up here in this first paragraph, what we've been told here is that d here is 200 nanometers. And this is the average amount it's spreading. So for our d squared in our equation, we're going to have to square this. Now, this is going to be equal to 2 times n. 2 is just a number. N is 3. So this becomes 6. This is then multiplied by the diffusion coefficient, which we can then find. And we're given the time over which it occurs. Like so. Now, one thing that I'm going to do here is we are going to convert everything to meters. This is going to help us deal with things later on. So a nanometer is just 10 to the negative 9. So this e to the negative 9 meters, and our nanosecond is just 10 to the negative 9 seconds. And the reason I'm doing this is because our cell radius is in micrometers, which is a different unit than we started with. Now, you can do this, and you can literally just use math to solve for the diffusion coefficient, d. All right, if you do so, right, just literally rearrange it and solve it. What I receive for d is 2.66 times 10 to the negative 7 meters squared per second. Right? So we have a d here that's an SI unit. So this d is unique to our RNA. D is going to be a property of the thing that's spreading and what it's spreading in. All right, so now that we have d, we can actually use this to figure out the second part of our problem here. So we're going to use d, and we're going to keep it as a constant that we know. For the second part of our problem here, what we're looking for is how much time is it going to take for this thing to spread 500 micrometers. So we're going to use literally the exact same equation. The only difference is here, we're looking for the distance it's going to take to spread 50 micrometers. Just like before, it's going to be equal to 6 times d, right, where d is 2.66 times 10 to the negative 7 meters squared per second. And the time period here, t, is what we're trying to find. Now, just like before, we're going to probably want to put everything in SI units. So 1 micrometer is just 10 to the negative 6 meters. And this is equal to 6 times d. Oops. and our goal is to find t. You can rearrange this and solve for t, and it will provide you with the exact amount of time, typically speaking, it'll take this RNA vector, I guess, to spread out throughout your entire cell. So it'll be about 1.6 times 10 to the negative 3 seconds. All right, so you can use a sample spread, or a spread of a small case, in which you measured how long or how far it spread in a particular time period, as well as how many dimensions it spread in, to figure out the diffusion coefficient for this particular type of system. And then you can use this diffusion coefficient to figure out the time it would take for it to spread new distances. This here should be a capital E, not little e. And this is basically what the CDC is doing right now. Uh, they can't obviously predict how far it's going to spread, but most of the assumptions that you see with the flattening the curve and everything else, these are Brownian assumptions, done in a rather similar fashion to what we just did here. They take a look at the spread in an isolated system, use it to estimate a diffusion coefficient or diffusion rate, and then they use that to make a prediction about the future spread. So this Brownian stuff is like relatively powerful. It works for pretty much all systems in which you assume that things just kind of bounce off each other and there isn't a real strong at-range interaction. But what I cannot stress enough is when you're solving these problems, be real careful with how you read them. This n here is always, just like with stationary, written in words in your problem. So what you need to do is picture in your mind how many dimensions can this spread out. Can it spread out in all dimensions, which would mean n is equal to 3? Is it confined to a surface, in which n is equal to 2? Or is it even, say, confined to a straight line, or a very linear path, in which case n is equal to 1?